Good morning to everyone present here. I'm Sangeeta Lakshmi, working as Assistant Professor in EC Department of R.M.K College of Engineering and Technology. Today we are going to see the Unit 4, that is Design of Arithmetic Building Blocks and Subsystem. This is Session 1. So what are the syllabus in the Unit 4? We can see here, that is Arithmetic Building Blocks, Data Path Unit, adders, multipliers, shifters, ALUs, and then the comparison between power and speed trade-off. Finally, we are going to start the memory structure. And first of all, we have to know what is data path unit, because in any digital processor, if we are taking the four important modules are IO blocks, memory unit, data path unit, and control unit. Out of these four, data path unit is very important block in the digital processor, because all the computations are performed in the data path unit by getting the data from the IO blocks, and after processing data in the data path unit, that will be that will be stored in the memory, and this all are controlled by the control unit. So the data path unit consists of adder, multiplier, shifter, multiplexer, everything. So in this, out of all the module, which is very important module is adder, because by using adder, we can design any modules. For example, multiplier is nothing but the repeated addition. So it also requires the adder. So next is the data path unit, which consists of register, adder, shifter, and multiplexer. Actually, always the data path unit is arranged in a bit sliced organization. What is mean by bit sliced is, for example, if you want to design the 128-bit data path unit in the digital processor, means we have to design the data path unit only for the 1 bit, then it will be repeated for 128 times, so that we can get the 128-bit data path unit in the digital processor. So here it shows the 4-bit data path unit starting from bit 0 to bit 3. So the data will be coming to the data path unit based upon the control signal to perform the operation like addition, subtraction, multiplication, shifting, or any operations in the logical as well as the arithmetic operation can be computed within a data path unit, and this will be given to the right hand side, that is data out. Going to see the adder unit. First of all, we have to design the adder in the, that is we have to design the adder in such a way that we have to optimize the unit, so that the power delay trade-off can be improved. So the optimization can be performed in circuit level as well as in logical level. So if we are going for optimization in circuit level, we have to go for mirror adder, transmission gate based adder, Manchester carry chain adder, as well as ripple carry adder. Whereas if you want to optimize the adder in the logic level, we have to go for carry skip or bypass adder, carry select adder, carry looker gate adder, and carry save adder. So these all the adders we have to see one by one. We can start with a simple adder unit, that is half adder, which consists of two inputs A and B, which produces the sum and carry output. So this shows the truth table, that is based upon our inputs, that is two inputs. So 2 power 2 combination 0 0 0 1 1 0 1 1. So based upon our input combination, it will produce a sum and carry. So the sum shows that we will be getting 1 1 only when A and B both are different. If A is 0, B is 1. When A is 1, B is 0. So that time only we are getting S equal to 1. That means it requires the XOR gate to getting the sum operation. Similarly, if you are seeing the carry out, you will be getting 1 only when A equal to 1 and B also 1. So that time only you will be getting the carry equal to 1. That means it requires the multiplication operation which is required and the gate. So it clearly shows. The next adder is full adder, which consists of three inputs. This clearly shows that the 3 inputs means 2 power 3 combination, that is 8 combinations. For 8 combination, you will be having sum as well as the carry out. So just you can compare the carry in as well as carry out. The first two combinations 000 as well as 001. In this combination, the C in is 0 or 1 irrespective of the C in. The C out is 0. That means it is called, the carry status is called as delete. Right? Another four combinations starting from 3, 4, 5, 6. These four combinations, if you are comparing carry in as well as the carry out, it clearly shows that whatever the carry in you are having, that will be propagated to the output side. Right? Here it is 0, here also 0. Here it is 1, here also 1. That means in this four combinations, it clearly shows that whatever the carry in we are having, that will be same is propagated the carry out. That's why the carry stated is called as propagate. The last two combinations, that is 110 as well as 111. In this, if you are comparing carry in as well as carry out, irrespective of your carry in, whether it is 0 or 1, that's not a problem, but carry out is always 1. That means it is carry is generated. So this carry status is called carry status. So this logic is very much useful for designing the adders based on the delete, propagate, generate model. So this expression carry out as well as a sum can be expressed in terms of a generate and propagate model. The carry out equal to G plus P into Ci, whereas G and P is the generate and propagate. Whereas sum is also a function of generate and propagate, which is equal to P XOR Pi. So with this introduction, we will wind up this session. The next class we will start with the triple carry adder.